All right, we're back, and this unit has been all about loops. Now we're actually transitioning into for loops. We'll do a little coding where we'll code perfect numbers, and then we'll hit a recap. When working with loops, counter variables are so common that most modern day programming languages provide a loop that implements the counter variable directly into the loop. Such a loop, known as a for loop, exists in Java. The stuff that's here in yellow is effectively what is required syntax, and the other parts have a lot of variance in them. But for the most part, A is where we're going to initialize a counter variable, B is going to be our condition, and C is where we adjust that counter variable. Let's take a look. I have an example here. This particular example will loop exactly 10 times, and all it's doing is printing off hello world. Like while loops, for loops are control statements, the same category as if statements. So the same stuff that applies to all control statements as a whole is going to apply to for loops. One such thing is that a for loop, is going to have a head or header, right? Everything up here I would consider the head. We're going to have a body as indicated by the curly braces. All control statements have this ability. The braces that indicate the body of the for loop can be omitted provided there is only one statement. This particular property was not very common with our while loop, but it becomes a lot more common with our for loop. Part of that is going to be because with our while loop, incrementing the variable was one of the statements that traditionally would appear in the body of the while loop. However, the for loop moves that, it becomes part of the header, so this is actually going to be a little bit more common of a possibility. The head of the for loop differs quite a bit from the head of an if statement or while loop. This first statement is usually, almost always, going to be used to declare and initialize the counter variable. There's some technicalities in there, but really I shouldn't even mention it. This is where we declare and initialize the counter variable. Right here I'm creating integer I and setting it to be 0. While I is the most common counter variable, any valid user-defined symbol can be used. In this example, I'm using x, but notice that I've changed the other things, such as the condition, and where we adjust our counter variable to kind of reflect that x is my counter variable in question. However, I is our favorite, so this is going to be what you see for the most part. The second is the actual condition itself, right? This was pretty much the only thing in the head of a while loop, but here in our for loop, it appears second. The last statement in the header of the for loop is used to adjust the counter variable. Notice I'm saying adjust the counter variable. The most common that you're probably going to see is just a simple I++, right? Where we're incrementing I by 1. But you could do other things. You could decrement I here depending on what you're trying to accomplish. Of note, that adjustment happens at the very end of the iteration. It's the last thing that happens. Let's see. Whenever we encounter our for loop, we're going to declare and initialize our counter variable. Then we're going to check the condition. So this is the first thing that happens. Like I got code coming in here. We see our for loop. We're going to declare and initialize our variable. Then we check it. If this is true, we will enter the body of the loop and execute all the statements that are there. At the very end, I'm going to come back up and adjust my counter variable. In this particular case, we would do an I++, so after the first iteration, I would now be 1. And we're going to, so it's very important to know that this is the last thing that happens. It's the very, very, very end. You don't particularly have control over that, right? With our while loop, you could actually move that adjustment around a little bit, but here with the for loop, it's pretty much the last thing that happens, right? We're adjusting our counter variable at the end of the iteration. Then we're going to check the condition again. This process of checking the condition, executing the body, if the condition is true, and adjusting the counter variable is the actual looping portion, right? So let's kind of go back through that just real quick again. I encounter my for loop. I'm going to declare and initialize my counter variable. I'm going to check it against the condition. If it's true, I'll enter the body. At the very end, after I executed all the statements, there's only one statement here, but it could be lots. After I've executed the statements, I'll come back up and adjust my counter variable. Then I'll check it against the condition again. If it's true again, I'll enter the body again, execute all those statements again, come back up, adjust the counter variable. So this is the portion that's actually looping. this only happens one time, right? We're only declaring and initializing I once, but this process here is the actual looping portion. If you kind of look at it in some type of visual diagram, it looks like this. We would encounter our for loop and declare our counter variable, check it against the condition. If it's true, we would do all the stuff that's in the body, adjust our counter variable, check the condition again. Right? Notice this part is what's looping, and declaring the counter variable, declaring and initializing, that only happens one time. We're going to keep looping until I hit a condition that is false. Ultimately, the for loop is just an alternate version of a while loop. I don't 100% have this to be true or know this to be true, but I've kind of fathomed that the while loop is the only true loop that exists, that whenever you write a for loop, Java's going to basically just translate it behind the scenes to be a while loop. So I would say that a while loop is the only loop that actually exists, and the for loop is kind of just an alternate syntax, an alternate version. But that's important to kind of keep in mind, because here I've got them side by side. This while loop and this for loop are functionally equivalent. There's going to be one small difference, which we'll talk about in just a moment, but these are basically identical, right? I'm declaring and initializing I one time in both loops. I have this condition. It's the exact same condition. I execute the statements. The last thing that happens in both loops is that the counter variable gets adjusted, gets incremented by 1, and we're then coming back up and checking the condition. So these are functionally equivalent. Realistically, for loops offer no real advantages over while loops other than the uniform encapsulation of counter variable related information in the header. What do I mean? Everything pertaining to the counter variable, its initial value. It's the stopping point of the loop related to the counter variable. How we adjust the counter variable, it's all right here. And that's kind of nice. With the while loop, it could be spread out, right? Now, this is only 2 statements, and I could, in just one shot, see everything. But imagine that we just got 200 lines of code in a while loop. And that's possible. Okay, that actually happens a lot with like video game loops and that sort of thing. But I basically have to go dig to find the stuff related to the counter variable, where right here, it's all right here, right? This leads students to like really love the for loop. You're going to end up doing a lot of for loops. Even when I really want you to do a while loop, you're going to be like, I want to do a for loop. For loops arguably have a small disadvantage compared to while loops, in that the counter variable does not exist outside of the loop. This is super important. I told you that these things were functionally equivalent, right? Here I have the while loop on the left-hand side and the functionally equivalent for loop on the right-hand side. However, notice that this counter variable is declared before the loop. It will continue to exist after the loop. This is a little weird in the syntax, but technically this doesn't exist. It only exists in the for loop. It's not being created and destroyed each iteration. It's just, it exists over the course of the for loop, but only the for loop. Meaning that once the for loop is finished, if I try to print off the final value for I, I'm going to get an error here. Okay. There's some workarounds for that, but that's the gist of it, right? If I need the counter variable afterwards, which happens, then a while loop makes some sense. If I don't need the counter variable, then the for loop makes some sense. Now, this actually kind of gives us a slight advantage in one little sneaky way. The fact that this counter variable exists for this for loop and then stops existing here can be a good thing if we have multiple for loops. I'm not talking about nested for loops. I'm saying we loop and then a little bit later loop again. The reason why this could be a slight advantage is because I get to reuse integer I. We like this. We like the consistency of having I as our counter variable and using it over and over and over again. The fact that this is kind of locked to this one for loop and stops existing here means that later on in my code, I could create another for loop that uses I, because it's a different I at that point, right? So advantages, disadvantages to be aware of. I promise you this will be a test question where I try to do this and you can't because it doesn't exist. Okay, with that in mind, let's code perfect numbers. There's a number file video here that talks about perfect numbers. It's kind of cool. I kind of recommend it. But I'm just going to tell you what a perfect number is. A perfect number is a number greater than 1 whose divisors add up to the number itself. 6 is the smallest perfect number, as its divisors, 1, 2, and 3, add up to the original number itself. Okay, we're going to write a program that prompts user to enter a number, then prints a message indicating whether or not the number is perfect. I've got IntelliJ. I'm ready to go. I'm going to go to File, New Project. I'm going to go Next, Next, and I'm going to navigate to the correct folder. Just my generic principles folder. But I'm going to name this one Perfect Numbers. I'm going to right click on the SRC, make a new Java class called Perfect Numbers. Okay, let's plug in a main method with PSVM, and let's implement scanner. I'm going to maybe indicate to the user what our program even does. This program determines if a number, we'll say x, is perfect. I'm going to use a print, not a print line. Please enter a value for x. Okay, so we have our original value. Here's what I want to do. I'm going to use a for loop, but I want to basically loop until I get to my number, checking for divisors. As we find divisors, right, 1, 2, and 3 are divisors of 6. As we find divisors, I'm going to add them up into another variable. After I'm done looping, I'm going to ask the question, does my sum equal my original number? Okay, so I've prompted the user. I'm going to save their number into X. I'm basically ready to start looping. I'm going to plug in my for loop syntax, which looks kind of like this. Right, we have the reserved word for, and then these 3 sections which we'll kind of fill in. This first part is going to be where I declare and initialize some type of counter variable. We like I. So I'm going to create I, start it at 0, but as you'll kind of see, the very first number that I want to test is 1, right? Like 0 is really not going to have an impact here, right? Taking 0 and adding it to this is not really doing anything. So I'm going to start I at 1. The next part here is my condition. I basically want to test, I kind of winked at the camera, I basically want to test every number up to the number itself. Like, I don't want to test, when I'm looking for divisors for 6, I don't want to test 6. That doesn't make any sense. So we'll say as long as I is less than our number that we're testing for, in this case x. Right, so we're going to, this is where I'm starting. This is where I'm declaring and initializing I. 1 is the first number I want to test, so that's why I've started it there. We're going to loop as long as I is less than x, the number that I want to test, and let's consider 6 as an example number. With each iteration, I'm going to be incrementing I at the very end. Okay, so here I have a for loop header. We're declaring and initializing our counter variable. This is our condition, and at the end of each iteration, we're going to adjust I. We're going to increase it by 1. What I want to do with each iteration is ask, is the current number, I, a divisor of my original number, x? If it is, I found a divisor, so I'm going to add it to some type of sum. I'm going to create this variable sum to kind of track my sum as we go, or my total. And as we're looping with each iteration, I'm going to ask the question, is the current number I a divisor of x? How do I know it's a divisor? Well, when I do the division, there is no remainder. So I'm going to take x, my original number, in this example 6, mod it by I. And if that is equal to 0, that is, when I do this division, there is no remainder, I have found a divisor. What I'm going to do is add it to my sum. Sum is going to be what it is currently plus the current divisor, which is I. You should know at this point that this is the same thing as sum plus equals I. I'll leave this as a comment though. And that's effectively it. Right? We're looping over this number range. This number range is effectively 1 to x, inclusive on the 1, exclusive on the x. Right? So we're going to loop over that number range, checking for divisors. If I find this, if this is true, this means that I is a divisor, D-I-V-I-S-O-R, of x. If so, I'm going to add it to my sum here. Okay. At the very end, if sum is equal to my original number, then I've found, then the number itself is a perfect number. So we're going to do a final check here, right? If our sum is equal to the original number, what that means is that the original number, x, is a perfect number. I'll say something to that effect. Otherwise, this means that the sum does not equal the original number. It's not a perfect number. Let's try this out, and I'll make some edits and then kind of explain our for loop. I'm going to right click in free space, tell it to run. So we'll test it with 6. Supposedly 6 is a perfect number. I'm going to run it again with something that's not a perfect number, such as 5. And we say that 5 ain't perfect. I'm going to try a couple other test cases. The number file one is all about 8128, which is the largest perfect number that, that they knew in antiquity, as he puts it. So we'll do 8128, and we'll see that that is a perfect number. Okay. So the things that I was going to talk about in terms of what we could adjust, take a look at this if statement. There's only one statement inside of it. I can get rid of these braces, right? It looks like this for loop has 2 statements in it, but the only thing that's actually in the body of the for loop is this if statement. That's one statement. So I could technically get rid of these things. I'm going to run it again. I'm going to try it with the number again. And we see that that is still a perfect number. Okay, so think about this. Our sum starts off as 0. We're going to use 6 as the example. We're going to check to see, right? We encounter our for loop. I gets created. It is a value of 1. We're going to ask, is 1 less than 6? That is true. I'll enter the body. I'm going to ask, is 6 mod 1 equal to 0? Is 1 a divisor of 6? It is. It goes in evenly. Right? So we'll add the current number 1 to our sum. That's the end of the iteration. We're going to come back up to an I++. Why don't I track these things? Right? After I do the I++, I is now 2. We're going to ask, is 2 less than 6? That's true. We'll enter the body. We're going to ask, is 6 mod 2 equal to 0? That's true. 2 is a divisor of 6. We'll add it to our sum. Maybe I should keep sum updated. Sum at this point is now 3. I've added 2 and a 1. That's the end of the iteration. We're going to come back up to an I++, meaning I is now 3. We're going to check the condition. Is 3 less than 6? That's true. We'll enter the body. We'll ask, is 6 mod 3 equal to 0? That's true. 3 is a divisor of 6. We're going to add 3 to our sum. So sum is now 6. That's the end of the iteration. We're going to come back up, increment I. It's now 4. Let's check the condition. is 4 less than 6? That's true. We'll enter the body. We'll ask, is 6 mod 4 equal to 0? That's false. 4 does not go into 6 evenly. You got some remainder there. So we'll skip over the if statement. There's nothing left. We'll come back up to an I++. I is now 5. We'll check the condition. Is 5 less than 6? That's true. We'll enter the body. We'll ask, is 6 mod 5 equal to 0? That's false. So we'll skip over the body. This doesn't happen. We're going to come back up, increment I. I is now 6. Check the condition. Is 6 less than 6? That is false, at which point we would skip over the for loop. Like we're finished, we'll exit the for loop. We would continue on. We would ask, is sum, which is 6, equal to our original number, which is 6? That is true, and so we say 6 is perfect. Okay. The one last thing that I would say here is we could maybe use a string to kind of clean this up. I've talked about before how we effectively have duplicate code here because we're printing twice, and really this x plus is repeated in both sections. Another kind of more important thing to talk about, and maybe you have encountered this through your prime lab that you just did, is recognizing that we don't have to test this entire range. We don't have to test I to x inclusive exclusive, because the largest that a divisor can be is half of the original number. What do I mean? I can make this more efficient. One way I can make it more efficient is that instead of testing this number range, we only really have to go through half that number range, right? Think about 6. Our largest divisor was 3. Okay, and it's going to be that way for any number. The largest divisor that can possibly exist is halfway through that number range. So I can change this condition and shave off a lot of iterations. We can say as long as I is less than or equal to half of the number. Right? In my example here that we've been working with, 6 is my original number. We'll divide that by 2. That's 3. So we'll say as long as I is less than or equal to 3. So that means I will have an iteration because of the equals when it is actually 3. So to show that this is working, I'm going to run it again. We will test 6. 6 is perfect. We're going to test 8128. We're going to see that that is perfect. And we'll test some number that's not even close. It ain't perfect. Okay. So this is perfect numbers. That's the gist of it. If you're looking to get a little bit more out of this, one thing you could do is add in another loop, right? So you would end up putting basically all of this in a loop. Put a loop there. And you would basically test a number range, right? You could test, through whatever, the max value of an integer, and test every number along the way to see, is this perfect? What about this one? Is this perfect? Is this perfect? As you can imagine, that can be pretty time intensive, but it's one way to basically search for perfect numbers. Right now, we're basically supplying a number and then asking if is it perfect, but you could basically nest loops and you could test over a number range to see if numbers are perfect. So that's kind of cool. Let's recap. For loops are a type of blank in the same category as if statements and while loops. For loops are a control statement. True or false, the braces indicate the body of a for loop can be omitted, provided the body consists of only one statement. This is true. This is a property of all control statements. It's the only reason why I even ask this question. True or false, the first statement in the head of a for loop is the loop's condition. This is false, and I'm going to ask you, where is the condition? Well, the condition is ultimately the second statement in the header, right? The first statement declares initialize the counter variable. The condition is going to be the second statement in that head or header. In a for loop, the counter variable is updated or adjusted at the end of each iteration. This is true, and you don't really have a lot of control over this. There's a little bit of nuance to that, but basically for the most part, the counter variable is adjusted at the end of the iteration. What is printed by the following code fragment? Ooh. Our answer here is 6. And what I'm going to do is actually pull up a notepad, and I'm going to do what we call tracing. Right? I'm going to follow the values here. Right? Product has an initial value of 1. I has an initial value of 1. I'm right here. We're going to check the condition. We're going to ask, is I, 1, less than 4? That's true. We're going to enter the body where we take our product, which is 1, multiply it by I, which is 1, save that back into product. My new value for product is 1. That's the end of the iteration. We'll come back up, do an I++. I is now 2. We're going to check the condition. Is 2 less than 4? That's true. We'll enter the body. We'll take our product, which is 1, multiply it by I, which is 2. We'll save that back into product. Product is now 2. That's the end of the iteration. We'll come back up, do an I++. I is now 3. We'll check the condition. Is 3 less than 4? That's true. We'll enter the body. We'll do product, which is 2, times I, which is 3. The new value for product is 6. That's the end of the iteration. We'll come back up, do an I++. I is now 4. Let's check the condition. Is 4 less than 4? That's false. We would break out of our loop. We're done. We print out the final value of product, which is 6. This is also a test question, right? Being able to trace the values over the course of the loop is actually super important. That is going to be the end of our 4 loops. I'll see you in the next one.